Good evening. Good evening. You're welcome to our lectures for today. Today we'll take a look at chemistry. And we are still treating kinetic theory of matter. And remember, we have three states of matter: solid, liquid, and what? Gas. So, in our last class, we stopped at boiling. And when we say boiling, we are talking about what? Liquid, right? Good. And we explain boiling point, right? Is that a chemistry note? Biology note? I thought you said you didn't come with it.
No, I said I forgot my biology now. The one you gave us
Okay. No, it's chemistry. Don't worry. So, and boiling. What did we define as boiling point? What did we define as boiling point of a liquid?
when the liquid vapor is equal to the atmospheric pressure.
Is temperature? Is a point? Is a temperature at which is a temperature. The boiling point is a temperature at which the vapor pressure of the liquid is equal to the what? Atmospheric what? Pressure. That's the definition of welcome. That's the definition of what? Boiling point of a liquid. Actually, at that temperature now the liquid will start doing what? Boiling. When the vapor pressure is equal to the what? The vapor pressure of the liquid is equal to what? The atmospheric what? Pressure. So that's boiling point. Now, so we go over to freezing and what? Freezing and what? Condensation. We go over to freezing and what? Condensation. Remember, our reference book for today is New School Chemistry by Oseiyo Ababio, 2016 edition, as revised by Elias Akpanisi and Herbert Igwe. That's our reference book for today. And we ask for the past question review. The reference book is Prep 50 Jam Chemistry. So let's look at freezing and condensation. When a liquid changes to what, especially when there's a decrease in temperature, and the liquid changes to what? Solid. That's what is called what? Freezing. Okay, freezing. So the temperature at which this occurs is the freezing point of the what? Liquid. Am I communicating? That temperature in which the liquid changes to what? Solid is the what? The freezing point of the what? The liquid. Actually, what happens is that if you cool a liquid, that's how you cool a liquid. If you keep cooling a liquid, cooling it to, as temperature is going down, you're cooling the liquid. To get to a point, the liquid will turn to what? Solid. Am I communicating? At that point, that temperature at which it occurs is the what? The freezing point of the liquid. Okay? And sometimes, in fact, it starts from the gas cell. That's how you cool a gas. If you cool a gas, it goes to a point, the gas does what? The gas changes to what? Liquid. Am I communicating? When the gas changes to liquid, what happens there is what? Condensation. Am I communicating? So condensation is change of when the gas changes from where? When the substance changes from gas to what? To liquid. But freezing is when the liquid changes from the what? Liquid to what? Solid. Am I communicating? So that's the basic definition of what? Freezing and what? Condensation. Now, but this is layman understanding, but let's describe this as chemists, okay? What actually happened at the molecular level. What actually happens at the molecular level? Now, remember when we discussed the Remember when we discussed the what is it called again? When we discussed the kinetic theory of matter in all, we said that the that the temperature is an indication of the what? The average kinetic energy of the what? Of the what? Of the what? The matter. Am I communicating? The average kinetic what? Energy of what? Matter is a measure. Temperature is a measure of the average kinetic energy of what? Matter. And we solve many questions in that regard. Can you remember? We solve many questions in that regard. Now, what actually happens? When If you compare solid to liquid to gases, the particles of the gases have the highest what? Kinetic what? Energy. Because they are at random what? Motion. They are among the three states of matter that the one that the more what? Energy. Am I communicating? Because they have conquered the intermolecular forces between the what? The particles. So they move the average kinetic energy is very what? Is higher than in liquid and what? Solid. Am I communicating? That's why if you cool a gas down, the gas will turn to what? Liquid. Because it will lose some of this what? Energy. Am I communicating? So decrease in temperature is also an indication of the loss of this what? Kinetic what? Energy. When something in motion loses its kinetic energy, what will happen? Is to slow down. True of us? True of us? Good. So now, that's actually what happens in what? Condensation. When these gases lose their energy, lose their what? Kinetic what? Energy, they will cool down. But remember that no energy is lost completely. In fact, they lose that energy to another substances close by. So if they lose energy to another substance, a cooler substances, they will do what? Cool down and they turn to what? Liquid. I think I gave you an example. I gave an example that day when I asked you a question. When I say, why is that if you bring out a bottle of Coke from the fridge and keep it in the room, on the table in the room, and leave it for some time, you notice that there's droplet of water on the body of the what? Of the bottle. Why? Where is that water coming from? Did the water come from the Coke inside? Or how? Did you pour any water on it? How come the water? I think I explained that, right? Oh yeah, help us. What happened?
The water vapor around the bottle.
Okay, we
That's
do.
the water now.
So what happens? How does it come to that extent?
Because water is in the air.
So how did it change to liquid?
Mm,
You've forgotten. I can remember vividly. I explained it and we also answered the question. What happened?
because it's losing some of its energy to the body
Which body?
of the bottle.
Good, because you know that the water, the moisture, the air, the water vapor around that room is at higher temperature. And the room temperature is is how many degrees Celsius? Room temperature is 25. Room temperature is what? 25 degrees what? Celsius. Now, because room temperature is 25 degrees, so this water that is gaseous at that particular room temperature is at higher temperature than the bottle you take away from the fridge. So if they eventually touch the bottle, the cool bottle, they lose what? Their energy. And if they lose their energy, they will condense. They will undergo condensation and become what? Liquid. That's why you see the droplet of the liquid on the bottle of Coke. Am I communicating? Good. So now this is an example of what? Condensation. Example of what? Condensation. Now, when the liquid itself, when you now get liquid, and liquid cools down, as temperature as it's cooling, the temperature is going down, that is losing more kinetic energy, and the particles of the substance, the liquid, are slowing down, and they eventually gradually turning into what? Solid. The temperature at which they now turn to solid is what is called what? The freezing point of that what? Liquid. Are we together? You're not putting anything. Why? You know it. So why are you not putting that thing? Huh? You don't know how to put down something when a lecturer is teaching, or you want me to take notes. No, learn how to put down things. It's very important. Okay. Try to put down things when everything is not about notes. Just try. This thing is in the textbook you're holding. I'm just explaining it. So as I'm explaining, there's some point you hear, you put it down. Okay. So now let us now, having described this now, let us now let us now define condensation. I will define condensation as what? As what? The change of what? Gaseous to what? Liquid. And I've defined the freezing. Freezing as the change of what? Liquid to what? Solid. But freezing point is the temperature at which it takes place. Please know the difference between freezing and freezing what? Point. Freezing point is the temperature at which this solid liquid changes to what? Solid. If you get water now, at room temperature, water exists as liquid. That's water you see. At least in this our what? Environment. Do you know that there's some part of the world you go to, the normal water they see is ice block. True of us. There's some part of the world you will go to, the normal water, just as you see your normal water here as liquid, their own normal water there is what? Solid. So if they need the liquid water, they will go and do what? Boil it to turn to liquid water they need. The same way here, if we need the solid water, we'll go and do what? Freeze it. True of us. Good. If they need liquid water, they'll melt the what? The solid, it will become what? Liquid. Here now, if we want the solid one, we'll go and freeze it so that it will return to what? Solid. True of us. So it depends on the way. So talking about here now, as we are here now, our own water is what? Liquid at room temperature. Are we together? Is what? Liquid at what? Room temperature. So the temperature at which this liquid turns to what? Solid. So if you want that liquid water to turn to solid, you go and put it in fridge. At particular temperature, it will turn to what? Solid. That is the freezing point. So know the difference between freezing point and what? Just freezing. The same way we noted the difference between boiling point and what? Boiling. Now, we have described melting, right? Please note this point, that the freezing point of a substance is the same thing with its melting point. Freezing point of a substance is the same thing as its what? Melting point. What it means is that the same temperature at which a substance changes from liquid to what? Solid is the same temperature at which that substance changes from solid to what? Liquid. Are we together? So the same temperature at which a solid changes from solid to liquid, that is the same temperature at which the liquid form will change to what? The solid form. What is the freezing point of water? What is the freezing point of water? 0 degrees Celsius. Okay? True of us. So water freezes at what? 0 degrees Celsius. So at that same temperature, ice block melts to what? Liquid. To ordinary what? Water. Are we together? So that's what I mean by that. The freezing point of a substance is something that is what? Melted point. Now, there's something I want. There's another concept I want to look at. Latent heat. Have you heard of the term latent heat? Huh? Latent heat. Physics. Have you heard of the term latent heat? Latent. You've not? Wow. Latent heat. This is SS2 physics now. Two of us. SS2 second term, right? So what happened? What happened in your school, Jude? Tell me, what happened in your school? Why didn't you do it in your school? Which school do you attend to?
St. Joseph Mission.
Huh? CKC. No, I don't believe it. You are the one at fault. You are not in class. I know you can't use no CKC. CKC is a good school now. It's not possible. Maybe you are not in class. You are done with them, right? When? 2022. Maybe you are playing that time. So now let me explain something. Remember I told you, let's use water as an example. Let's use water as an example. Let's use water as an example. Or any substance, any solid substance. If you get a substance that is in solid form now, look up. If you get a substance that is in solid form and heat it, if you are heating that substance, you are impacting energy into it, into the molecules of the substance. True of us, because as you are heating it, you apply heat energy. Remember, energy is not lost. Instead, energy is converted from one form to the what? Another. So that heat energy you are applying to that substance is transformed to what? Kinetic what? Energy. So the particles of the substance will gain the kinetic what? Energy. Remember, in solid form, the particles are together. They have strong intermolecular what? Force of what? Cohesion. That's why solid is like this. Solid is what? Look up. Solid is like this. The particles are like this. That's why it is strong. It can have a definite shape and volume. Am I communicating? But when you apply this heat you apply in this solid will transform from heat energy to what? Kinetic energy. And the particles of that solid will gain it as what? Kinetic energy. And they will start vibrating and start breaking away from their what? Bonding, their intermolecular forces that hold them what? Together. They'll start breaking away. And before what's going on, as this heat, first of all, as you apply the heat, as you apply the heat, the more heat you apply, the temperature, the melting cannot take place. Boom. The particles will be gaining this energy. As they're getting more energy, then as you apply more heat, temperature is increasing. They're getting more energy. The temperature is increasing, and they're getting more energy. It will get to a point. They will get the energy that will be above that will be enough to conquer the molecular forces holding them together. Am I communicating? Now, when they get that energy now, they will now break away from each other. Now, but as the temperature is increasing, it will get to a point, the temperature will stop increasing. That's what I want to explain. You are still applying heat too. The temperature will stop increasing. The temperature will remain constant at a point. Do you know what happens there? They have gotten enough energy at that point. Now they want to start breaking away from the what? Breaking from the intermolecular forces holding them. You are still applying more heat too. You are still applying what? More heat. As that heat that is applied is not increasing the temperature again. Instead, that heat that is applied will now be used to break that what? Intermolecular what? Forces. That heat applied there is what you use to break down the intermolecular forces. The heat is hidden. Okay? It's hidden heat. And the word latent is same thing with what? Hidden. Am I communicating? So that is latent heat. That's what that latent heat, you can call it latent heat or hidden heat. That is the heat energy that is used to break down the what? Intermolecular what? Forces. Am I communicating? That is the latent heat, hidden heat. That heat is not, you cannot detect it in thermometer as an increase in temperature, because it's used to break down the intermolecular forces. So when this latent heat occurs in the conversion of solid to what? Liquid, you call it latent heat of what? Fusion. Is it clear? So when this heat is involved in the conversion of solid to what? Liquid, we call it what? Latent heat of what? Fusion. Now, When this, see what happens. See what happens again. As when this as you keep hitting that thing, you will not see it as increased temperature. It will be used to break down the intermolecular forces. Then it will get to a point when the intermolecular forces is broken down, the solid will now turn to what? Liquid. Am I communicating? Will now turn to what? Liquid. You see that the solid has done what? Melted and becomes what? Liquid. Now, immediately the solid turns to liquid, you start seeing increase in temperature again. You start seeing increase. Remember you are still applying heat. You start seeing increase in temperature again. If you don't stop the application of the heat, and you keep hitting it, do you know what happened? The temperature will be increasing the more. It will be increasing the more, and the temperature will keep increasing, until you get to a point where, do you know that temperature is increasing? That the molecules of the liquid that is formed is gaining more energy as the temperature is increasing. It also get to a point where the liquid molecule now will now get more energy that will even in liquid state there are still intermolecular force, but it's not strong as that of the what? Solid state. Now it will get to a point where this liquid will get more energy that will help them to break away from anything that's holding them at all and be free like what? In gases. Now, when you get to that point where this liquid is about to, the particles of this liquid is about to break up from the intermolecular forces, this heat again will, the temperature again will be what? Constant again. That heat you apply at that point in time will be used to break down the intermolecular forces holding the liquid molecules what? Together. The temperature remains constant. But when all the molecules of the substance has broken down and they are on their own, they are free in gas, immediately the solid changes, the liquid changes to gas completely, you start seeing increase in what? Temperature again. Am I communicating? So this is what happens in what? When substances move from solid to what? Liquid and to what? Gases. So that heat that latent heat used in breaking down these forces in cohesive forces in liquid before they change to gas is called what? Latent heat of vaporization. It's called what? Latent heat of what? Vaporization. So we have latent heat of fusion. We also have what? Latent heat of what? Vaporization. So vaporization is nothing but when this liquid turns to what? Vapor. Okay? Vaporization is whereby the liquid turns to what? Vapor. Now, the heat that helps to achieve that hidden heat, that latent heat that helps to achieve that is called what? Latent heat of what? Vaporization. Are we together? Are we together? Good. So, that's exactly what happened. Okay. Sometimes you see a graph. Look at this graph. Look at this graph. As you can see here. Can you see this is temperature, right? Axis. And this is what? Time. Take it. The ice was originally at what? 0 point at -5 what? Can you see -5 here? This is ice. The ice they use ice as a case study here. The ice is at -5 degrees Celsius. Now, if you heat it now, the temperature will increase to what? 0 degrees Celsius. Remember, the melting point of ice is what? 0 degrees Celsius. True of us. And the freezing point of water is what? The same what? 0 degrees Celsius. Because the melting point of a substance is set as its what? Freezing point. Now, when you get to this 0 degrees Celsius, the ice will turn to water. But here, there's a mixture of ice and water. True of us. It's turning. Now, the heat, can you see that the temperature is at 0? The temperature is constant. Even though the time of heating is increasing, you see that it's constant. It didn't increase. That is where the latent heat is. This is latent heat of what? Fusion. Because the heat applied, cannot be seen as increase in temperature because it is used to break down these what? Forces. But when the substance has broken down the forces in the ice, which is solid water, and it turns to liquid water, temperature will start increasing again because you are still applying heat. Temperature will start increasing again. It will get to 100. You know that the boiling point of water is what? 100 degrees stage. When you get to the boiling point of water, see it here. The temperature will remain what? Constant again. This means that this horizontal line means that the temperature is what? Constant. Do you know what happens here? The heat applied is hidden here. It's used to break down the intermolecular forces in liquid water. So the heat here cannot be detected in the what? Thermometer, because it's hidden. So the heat involved here is a latent heat of what? Vaporization, or the hidden heat of what? Vaporization. Why heat here is what? Latent heat of what? Of what? Fusion. Is it clear? Are you sure? Good. So this is exactly what happens. Now, with this down, I think we are good to go here. So if you want to put down something, you can simply say that latent heat of fusion is the heat energy. Is the heat energy required to overcome. Latent heat of fusion is the heat energy required to overcome the cohesive forces during what? Melting. You can say that latent heat of fusion is the what? The heat energy required to overcome the cohesive forces. You know what cohesive forces are, right? Forces that hold the particles together, right? So latent heat of fusion is the heat energy required to overcome the cohesive forces during what? Melting. While latent heat of vaporization is the heat energy. Latent heat of vaporization is the heat energy required to overcome the cohesive forces during boiling. Latent heat of vaporization is the what? The heat energy required to overcome the cohesive forces during what? Boiling. Remember I said that the latent heat cannot be detected using what? Thermometer, because they are hidden heats. Okay? They are hidden heats. They don't contribute to the rise in temperature. Instead, they are used to do what? Break down the what? Intermolecular what? Forces. Are we together? Are we together? Good. So with this now, let's move into another thing. Let us now look at this kinetic theory. We have discussed kinetic theory, but you cannot see these particles with your eyes. So, but there are some phenomena that what support the kinetic theory that you can use to prove this kinetic theory. So we look at the phenomena that support what kinetic theory. We have phenomena like Brownian movement, diffusion, osmosis. Brownian movement, diffusion, osmosis. Brownian movement, diffusion, osmosis. Brownian movement, diffusion, osmosis. So these are some phenomena that you can use to do what? Support what? Kinetic theory. Now let's look at this. Let's look at this phenomena one after the other. Let's start from what? Brownian what? Movement. Actually, this movement was first observed by Brown. And that Brown was a botanist in 1827. It was first discovered by who? Brown in 1827. So how did he come up with this? How did Brown come up with this? Actually, Brown was carrying out what? experiment with what? Pollen grain. And he noticed that when you put pollen grain, when you put what? Pollen what? Grain in water or in a medium, he noticed that this pollen grain, they move in a zigzag manner, like this. Look at it. Like this. Look at it. Hello? They move in a zigzag manner, as if something is hitting them, okay? Making them not to move in a straight line, as if something is disturbing them. Now, that's what he discovered. So they move in zigzag what? Manner. So this became an issue. How? What causes these particles to move in this zigzag manner? So further experiments came to realize that there are something in that water at particular level that is hitting this, hitting this what? Hitting this what? Pollen grain. Pollen grain is not heavy, it's light. So for you to move like this, there's something that is hitting it. And when that hit it, it will change direction and move like this. As you move like this, another one hit it, it will move like this. As you move like this, another one hit it like this. This is how it keeps moving. That means this liquid has what? Particles, molecules that are what? Hitting this what? Pollen grain to make it to move what? In a what? Zigzag manner. So this is a very important movement that explains what? Kinetic what? Theory. Are you together? Are you together? So, had it been there is nothing that is hitting this pollen grain, it will not be moving like this. True of us. Something hitting it. Just like as you are in a car going like this, going straight, and another car hits you. Do you think you continue in that direction? You move like this. True of us. The same way this pollen grain are moving on there, but as they move, they hit by heavier molecules, okay, that will make them to do what? Change direction as if they of course the weight is not much, as if they are being tossed around by this what? Molecule. This shows that this liquid has what? Particles. Am I completing? They have particles. And these particles are also a continuous what? A movement too. So this what explains, this is how kinetic theory explains what? Brownian what? Movement. This is how kinetic theory explains what? Brownian movement. So let's look at diffusion. Diffusion. So, how do you think diffusion, how do you think it supports kinetic theory? Diffusion. Oh yeah, I'm listening. How do you think diffusion supports kinetic theory? Just can see. How do you think diffusion does that? How? I'm listening now. You are you following us? Are you sure? Answer me now. How do you think diffusion explains kinetic theory? Sorry, I mean, how do you think it supports kinetic theory? I've explained the Brownian movement. So tell me about diffusion. In the first place, diffusion. In diffusion, there's movement of what? What is this? in the first place, there is, okay, let me use what you know. Let's assume, let's assume you are here. You do that. You do this one almost at least if not for anything once in a week. You are here, right? I'm here now, right? Right? And I gas. I'm here, right? I release the gas here. Give it not more than 10 seconds or 3 seconds. You start to do what? True of us. How did what I released here, the bomb I released here, get to you then? How? From here, you can perceive it. How? 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 It moves from here to here. There. That's what diffusion. True of us. It has higher concentration here. True of us. And it's a lower what? Concentration. So this concentration gradient will make it to move from here to what? There. All together. Now, without the air and the particles, the air particles and what are the in this environment, do you think this can get to you? Huh? Huh? Do you think? Good. Now this explains how diffusion supports what? Kinetic wave. But the particles of the molecules of the air is at constant what? Motion. True of us? Constant what? Motion. And because of this thing now, this thing can easily be carried from here to where? There. True of us? True of us? Now, so that's what happens with what? Diffusion. And that's how diffusion, you know, supports what? Kinetic what? Theory. That's how diffusion, you know, supports what? Kinetic what? Theory. Now, diffusion doesn't only occur in gases. You can have diffusion in liquids. So, in fact, you have the direction in gases, direction in liquids, and direction in what? Solid. It shocked you. You have diffusion in what? Gas. Huh? I will explain. We have the diffusion of what? Solid. Diffusion in solid, diffusion in liquid, and diffusion in what? Gas. So what actually happens? What actually happens? What actually what happens? You see here that the diffusion describes the movement of what? Solid particles from where? Through a medium. From a region of higher what? Concentration to a region of what? Lower what? Concentration. Diffusion describes the movement of solid particles through a what? Medium. From region of what? Higher concentration to region of what? Lower what? Concentration. All together. So what it means is that these solids can move from where it is higher concentration here to where it is what? Lower concentration. Now, if you buy perfume now, inside that bottle and around you, it's at higher. The perfume is what? Higher what? Concentration. True of us. But if you release the perfume, it will come close to you. Here now is at lower what? Concentration. All together. So this is exactly what happens. In what? Diffusion. Generally, this what happens in what? Generally in what? Diffusion. Now, let's look at diffusion in gases. Actually, diffusion is fastest where? Where? Which state of matter does diffusion? Okay, good. So diffusion in what? in what? The gases is the fastest, very fast. After I think I have explained the reason, right? Remember, when I said that gases has the particles of gases have more, the highest what? Kinetic what? Energy. Can you remember? I said that the particles of gases have higher what? Level of what? Kinetic energy. So the energy of the particles in gases is more than that of the what? Solid and what? Liquid. That's why diffusion. Because the particles move at a higher what? Speed. So they can move, they can carry the whatever that enters them, whatever that is released fast, very fast to here, to where the that is not what present altogether. So that's why I said that what diffusion in gases also support. Okay, with this now, do you think diffusion in gases supports kinetic theory?
Yes.
Because you can use it to explain what kinetic what theory in the aspect of the rate at which the gaseous particles move. True of us? Good. Then let's look at what of diffusion in liquid. Diffusion in liquid is slower because the gases has lost what? Their energy, right? So they have slowed down. So diffusion in what? Liquid is what? Slower than that in what? Gases. But it's faster than that in what? Solid. Altogether. Diffusion in liquid is slower than diffusion in what? Gases. But diffusion in liquid is faster than diffusion in what? Solid. Okay? Of course, you know the reason why they are faster now. They are slower because they have what? Less kinetic energy than what? Gas molecule. True of us, they have less kinetic energy than what? Gas molecule. You also know the reason why diffusion in in solid is slower than diffusion in what? Liquid. Because in solid, diffusion in solid is slower than that of what? Liquid. Or you can say that diffusion in liquid is faster than that of what? Solid. Dual reason because in solid the kinetic energy, in fact, they are resting. They have the kinetic energy is lower in solid than in what? Than in what? Liquid. Are you together? Are you together? Good. Now, let's look at what? Solid. One may wonder, how come diffusion, how come you say that diffusion takes place in what? Solid. Actually, why you look as if there's no diffusion in what? Solid? Do you know the reason? Because diffusion is very, very slow. Solids can take years before they can diffuse. Okay? The diffusion in solid is very slow. So the process of diffusion in solid is very extremely slow. So now, if you want to understand this now, just get a gold bar and silver bar. If you go to a gold bar and silver bar, tie them together with rope. Just tie it with anything so that they have contact with each other and keep it for like 1 year or 2 years. If you go back, you will notice that some particles of the gold has entered that there's a mixture of the particles between the gold and what? Between the gold and what? Silver. All together. So that proves that what? Diffusion also occurs in what? Solid. That diffusion also occurs here in what? Solid. So let's look at osmosis. How does osmosis support what? Kinetic theory. How does osmosis support kinetic theory? How? How does osmosis support kinetic theory? Now let's look at it. We have described that diffusion supports kinetic theory, right? Good. Then how does osmosis support kinetic theory? Now listen. Even though if you look at the definition of osmosis and diffusion, if you look at it, they are different. But are you aware that osmosis is a special type of diffusion? Osmosis osmosis is said to be diffusion, but a special type of diffusion is called what? Osmosis. So what makes it what? Special. Now, listen. Let's use water molecule as an example now. Did people do that thing in biology where you peel a yam? You peel a yam and pour either salt solution inside the water and make a hole in the yam, right? And pour and pour salt solution, mix salt and water and pour inside that yam, that hole you made in the yam. You have peeled the yam so that you can expose the inside. Then you carry the yam and put in a basin that contains what? Water only, not salt water, just water. You will realize and mark the level of the water inside the yam and the level outside the yam. If you keep it and come back tomorrow morning, you will realize that the level of water inside the yam has increased, while level of water outside has done decreased. What happened is that the water will leave the outside and enter the inside. This through the process of osmosis. Now let me tell you why osmosis is a special type of diffusion. In osmosis, in the diffusion generally, right, the substance move from region of lower concentration to where? Move from the region of higher concentration, right, to the region of what? Lower. Are you following? In diffusion, we know it moves from region of higher concentration to where? Region of what? Lower concentration. Now, in osmosis, that water that move from outside to inside, did it move from area of higher concentration of water to the area of lower concentration of water, or did it move from area of lower concentration of water to the region of higher concentration of water? What happened? That water that moved from outside and enter inside that pit, what happened? Did it move? Is it from the area of higher concentration of water? If the water outside, if you compare the water outside the yam and the one inside the yam, which one is more? Inside is more. Remember that hole is small, right? Is one outside, right? Now, outside, apart from that, the one inside is not ordinary water. It's a water salt solution. Okay? On its own is concentrated, but we're talking about concentration of water that is moving. That substance that is moving is what? Water. The salt is not moving. What moves is that substance. What moves here is water. So that water is the substance in question. Moves from outside the yam is less concentrated of the solute, but high concentration of water. True of us is outside. True of us. But inside, what you have inside is what? High concentration of the solute and almost nothing for what? For what? Are you with me? Let me explain again. I'm trying to explain the reason why I said that the osmosis is a special type of what? Diffusion. In diffusion, the gas is here, right? The gas here is high concentrated. The gas will move from here to there, where it is lower concentration. That one is called what? Diffusion, right? But in this osmosis, what is moving there? Is it water or the salt that is moving? What is moving? Water. In osmosis, the water is more outside, right? So outside, water has higher concentration outside than inside, true of us. Now the water inside is smaller, but the water is moving from a region of higher concentration of water to region of lower concentration of water. Is that not the diffusion? So that's why I said that osmosis is a special type of what? Diffusion. Are we together? So if osmosis is a special type of diffusion, you don't be told that this is also what? It also supports what? Kinetic what? Theory of what? Matter. Are we together? Are we together? You don't be told that it also does what? Support the what? Kinetic theory of what? Of what? Matter. So with this now, you don't be told that osmosis also support what? Kinetic what? Theory of what? Of matter. Any question? Ask me. Ask your question. So if you study this osmosis, you'll be very and understand it. You will see that what is it called? You will see that that osmosis support what? Kinetic theory of what? Matter. So with this now, I want us to actually look at gases. We look at gases. We'll study what gases are. So we cannot study gases without looking at kinetic theory of gases. That this kinetic theory of gases is just an assumption. Assumptions of the what? Kinetic theory of what? Gases. So we know we have the gas we call ideal gas, and we have the one we call real what? Gas. Have you heard of such thing before? Huh? Huh? Kind of ideal gas. There's one we call what? Real gas. So many scientists have actually looked at what? Studied what? Gases. So gases have been studied extensively by scientists like Boyle, Charles, Graham, Downton, and what have you. Boyle, Charles, Graham, and Downton, etc. So let's look at absorption of this kinetic what? Theory of what? Gases. So this theory, number one, say that the gas molecules move randomly in a straight line. It said that the gas molecules move randomly in what? In a straight line. Colliding with what? One another. And with the walls of the what? Container. So the gas, if you put a gas in a container now, the particles are always filled with energy. So they move in what? In what? They move in what? Straight what? Line. Randomly and in what? Straight line. And as they move, they do what? Collide with each other. With one another. Are we together? As they move, they do what? They collide with what? One another. They also collide with the wall of the what? Container. Are we together? They collide with one another, and they also collide with the what? Wall of the what? Container. They collide with one another, and also collide with the what? The wall of the what? Container. Are you together? Are you together? Now let's assume let's assume you have you are moving like this, and I come and hit you. You lose your energy. Three of us, you lose your what? Energy. First of all, you fall first, or at least nearly what? Fall. But if you are moving at a high speed, you can't continue with that speed again. You slow down. Two of us, good. That's what happens when molecules of these particles of these gases, this gas in the container, when they are moving in straight line, they collide with each other. One may collide one, it go like this. Collide another one, it go like this. This collision with one another makes them to what? Lose what? Energy. And that's why they move at different rate or speed. Because the particles of this, they move with different levels of energy because of what? The collision between them. Then when as these particles is hitting, look up, as these particles are hitting the wall of the container where you put them, and they hit the wall of the container, inside here is the container, as they move and hit the wall of the container, they are exerting, there's a force. The force will hit at this particular area. Remember the meaning of pressure. Pressure is force per unit what? Area. Remember, right? Pressure is force per unit area. And if they hit on the wall of the container, they will exert pressure on the wall of the what? Container. Okay? So the particles of what? Gas, they move in a what? In a straight line, randomly, colliding with what? One another. They collide with what? One another. And they exert pressure on the wall of the what? Container. Does it make sense? Eh? So that's what happened in what? The first what? Absorption of what? Kinetic theory of what? Gases. The next one, say that the collision of gas molecules are perfectly what? Elastic. The collision of the gas molecules are perfectly what? Elastic. What do you mean by this being elastic? Now listen. I've said before now that if you have two molecules or more, they will hit what? Each other. One will slow down, another one will what? Faster and do what? Going straight. Now, be that in mind, you realize that this collision of these molecules, as they hit, one thing there is that if they hit the wall, they will not lose energy. They will do what? They will rebound. Okay? They will rebound. Once they hit the wall, bam, they will do what? Rebound with the same energy. They will fall back with the same what? Energy. That's why we will say that they are what? They are what? That's why I said that their collision is what? Perfectly what? Elastic. Is what? Perfectly what? Elastic. Please know this point. The collision of gas molecules are what? Perfectly what? Perfectly what? Elastic. So that's what happened. What happened in the collision? What happened in the second assumption of the what? Kinetic what? Theory. What of the third assumption? Remember, we say that gas molecules, these particles are tiny. Hope you know. And if you want to compare if you want to compare the volume of these tiny gas molecules, compare with the volume of the entire what container, you will realize that that volume of that gas molecule is what that volume is negligible. You can neglect it. You can overlook the volume, because the volume they compare, what each of them the volume each of them occupy, when compared with the entire container, is what you cannot compare the two of them. It will become, in fact, it is what negligible. So in that frame, in that way, you now realize that the gas molecule, you are trying to point out that these gas molecules, they are what? Small. That's what I'm trying to point out by this now within now. The volume is to occupy is very what? Small. To compare with the volume of the what? Entire container. Remember that these gas molecules have broken away from the intermolecular forces, true of us. So that means they are free. And the space between them is small to compare with their size. The space between between molecules of a gas are what? The space is the distance is more to compare with the volume of the volume of the gas. So that means you can neglect that. The volume is what? Negligible. Okay. Are we together? Good. Under assumption is what? Do you agree with this one? Let me know those that think. He said that the cohesive forces between the gas molecules are negligible. True or false? The cohesive forces between the gas molecules are what? Negligible. True or false? Huh? It's true, right? Yes, now. Yes, I agree. The cohesive forces between them. Remember that the gas molecule are no longer held together. True or false? True or false? So the cohesive forces can be overlooked because it's not. Am I communicating in gas molecule, because they are far away. So the forces it cannot attract them like that because they are far away. So that means the cohesive forces in that the cohesive forces that tend to hold the molecules together, which is not easy for gases. It can be it's negligible for gas. Does it make sense? Is what? Negligible. Is what? Negligible. I agree with is what? Negligible. So the cohesive force is what? Negligible. You can ignore that. That's the point this fourth assumption is trying to let us know. The fifth one, I think I have mentioned this yesterday. When we take kinetic theory of matter, that the temperature is the measure of what? Average what? Kinetic what? Energy of the what? Particles. So temperature, do you agree with this one now? Based on what we did last time, that the temperature of a gas is a measure of the average what? Kinetic energy of the gas particles. Do you agree with me now? Do you agree with me now? Yeah, because do you know why? Increase the temperature. Will they get more kinetic energy? That's it. Increase the temperature. Will they get more kinetic energy? Bring down the temperature, they will lose more energy. True of us. So that's why I said that the temperature is what? A measure of the what? Average what? Kinetic energy of these what? Particles. Now these are the what? 5 assumptions of the what? Kinetic theory of what? Matter. Not matter now, gases. Okay? Because you have entered what? Gas. Now, when I was describing that the gas particles hit the wall of the container and come back. Okay? Hit each other and do what? Well, when I was saying that, I talked about the what? Pressure. Is that thing they hit on the wall and come back and hit each other? That the pressure that is being what? Pressure that is being what? Is the pressure exerted by this what? Gas particle. So now, imagine, I'm talking about just one of the particles here. Imagine millions of particles exerting such force on the wall and on each other. What will happen? Pressure will do what? Increase, right? Right? Because the particles are hitting a mass. They are hitting on the what? On the what? They are hitting on the wall of the what? Container, and are colliding with what? Each other. So this is what we mean by pressure that is exerted by what? Gases. On a general note, in your physics now, let's look at this a bit quantitatively. In your physics, SI unit of pressure is what? Of pressure is what? Is it not Pascal? Pascal, which is written as saying Newton force over what? Area, right? Newton per meter what? Squared, right? But the name given to it is what? Is what? Pascal, PA. Good. So also you this pressure, gas pressure, is also measured in millimeter what? Mercury. Hope you're putting down these possible units. It can be measured as what? As what? In millimeter what? Mercury. It can also be what? Have another unit we call atmosphere. Sometimes you see one, maybe they will write something like this, 1 atm for you. That atm means what? Atmosphere. Is the what? The unit of what? Pressure. Okay? You see atmosphere. You can also see another one. Millimeter mercury is also used to do what? Measure what? The unit for what? Pressure of what? So what is the relationship between now atmosphere, millimeter mercury, and what? And the what? Pascal, which is Newton per what? Meter squared. Actually, 1 atmosphere is equal to 760 millimeter mercury. You're lost. Huh? Where?
Okay, I'm recording it later.
No, you can ask a question. Feel free.
No, don't worry, I'm understanding.
Okay, you're following. Good. Now, I said that when I mentioned 3 units, right? Atmosphere, meter mercury, and what? Pascal, or what? Newton per meter squared. I said that there's a relationship between 3 of them. 1 atmosphere is equal to what? 760 what? Millimeter what? Mercury, which is equal to what? Which is equal to what? 101,325 Newton per meter squared. 101,325 Newton per. That's why you see some units, they'll tell you 1.002 or something. Times 8 to what? 5. Have you seen something like that as a unit of pressure in your physics? Are you there? This is where it came from, okay? Now, sometimes you also see it as what? As a millimeter mercury. But just know that 1 atmosphere is equal to what? 760 what? Millimeter mercury. Which is equal to what? 101,325 what? Newton per meter squared. Are we together? Are we sure? Good. Now, let's continue. Please, if you have any question, ask. Feel free to ask. Now, let's continue. So, having done that now, let us now pick up this gas law. We are moving to gas laws now. Okay? We are moving to what? Gas laws. We are moving to what? Gas laws. We are moving to what? Gas laws. So what about the gas laws? What are these gas laws? So remember I told you that these scientists worked on the nature of what? Gas. Remember, I mentioned the name, right? Boyle, Charles, Graham, right? Who else? There are many of them. Who else? Dalton also worked on it. Two of us. Remember Dalton's law of partial pressure. Remember. So now let us now start with the first one. After this law, we will now stop and look at our past question. See what we can do before it's 6 p.m. Okay? Good. Now let's look at Boyle's law. So what happened in Boyle's law? And who is this boy? What is his full name? His name is what? Robert what? Boyle. Robert what? Boyle. Okay? Robert what? Boyle. So this man stated this law in 1662. When? In 1662. So what happened? This law talks about the relationship between, this law actually talks about the relationship between the what? The the pressure of what? Gas, and the what? Volume of what? Gas at constant what? Temperature. Okay? The law talks about the what? The relationship between the volume of gas and the pressure of gas at constant what? Temperature. That's what the law talks about. The relationship between the volume of gas and the pressure of gas at constant temperature. The relationship between the volume of gas and pressure of gas at constant temperature. So now, what is that relationship? What is that relationship? What is the relationship between the volume of gas? How do they vary with each other at constant temperature? Now, this will lead us to what? Boyle's law. So Boyle's law states that the volume of a gas, the volume of a given mass of a gas, Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure, provided that the temperature remains what? Constant. You can state this law you must not follow this, okay? This is exactly how it is quoted in Ababio. But you can simply say Boyle's law say that at constant temperature that the volume of a given mass of a gas varies what? Is inversely proportional to what? The pressure of the what? Gas. Simple. But let's follow the one here. He said that Boyle's law states that the volume of a given mass of a gas is inversely proportional to what? Its what? Pressure. Provided that the temperature remains what? Constant. Are we together? Are we together? Provided that the temperature remains what? Constant. So that's what Boyle's law states. So in essence, you can say that if you want to state this law, what it means is that if you want to state this law mathematically, V is inversely proportional to what? P. Hope you know how to state this inverse proportionality sign. V is inversely inverse. What if V is inversely proportional to P? How will you write it? V, that sign and what? No, if you write P, it's direct. If it's inverse, inverse of it is what? Good. What 1 over P? Is it clear? Is it clear? So if you want to write it mathematically, V is inversely. You put that sign of what? You know what I'm talking about, right? You put the sign of proportionality, then write 1 over what? P. But you cannot solve any calculation with that sign. We have to remove that sign. And for you to remove that sign, you introduce what is called what? Constant of what? Proportionality. So if you put constant K, it becomes that V is now equal to K over what? P. Are we together? Are we together? So you can find the K. So K is now equal to what? V, PV, true of us, PV. So what it means is that the product of a gas, you can put this one down. The product of the pressure of gas and volume of a gas at a given temperature is constant. That's why PV is equal to K. If V is inversely proportional to if V is inversely proportional to P. That is V sign of proportionality 1 over P. And if you put constant, it becomes V is equal to what? K over P. Make K the sort of formula. Be doing it as I'm explaining. If V, put that sign of proportionality. Hope we are doing it. Then 1 over P. Right? Now, remove that sign of proportionality and introduce K and equal to. So V is now equal to what? K over P now. True of us. Hope you are doing it. V is now equal to what? K over what? P. Now make K the subject of the formula. K is now what? Make K the subject of the formula. K is now what? Oh yeah, make K the subject of the formula. Cross multiply now. No. No. Let me see what it is. No. You don't know how to change sort of a formula. No. That's what are you doing? Don't you know how to do cross multiplication? Cross multiply, let me see. I think it's time I get a board is very important here right now. Very, very important here right now. So I can write these things. Yes, now K is equal to K PV now. K is PV now. If you don't know how to do change of subject of formula, hey, that's the problem now in calculation now. That means you'll be having issues in anti-calculation. Forget it. If you don't know how to do change of formula, subject of formula, then you'll be having issues in calculation. Whether in chemistry or any calculation, you will have issues. This thing, is it not? This thing is like this now. Look at it now. We have said that we have gotten that V is equal to what? K what? P. Hope you know that this. Hope you know that this is written as saying V over 1. Hope you know. Do you know? It's equal to K what? Cross multiply. This one times this one. This one times this one. We have that K times 1 is equal to what? P times what? V. So K times 1 is what? K. K is now equal to what? PV. Oh yeah. Let me see this one. Sorry. Let me help see. Here, this is you already know that V is equal to what? KP, right? Are you aware that this is written as V over 1? You cross multiply, is it not? K times K. K times what? 1 is equal to what? P times what? V. This multiply this and this multiply this. K times 1 is what? K is equal to P times V is what? PV. It's not true. So, what this means that at any point at constant temperature, the product of the pressure of a gas and its volume is what? Constant. True of us? So the product at a given temperature or constant temperature, the product of the pressure of a gas and its volume is what? Constant, K. So what it means is that if at any temperature, the product of the pressure of a gas and its volume is constant, that means from one state, let's say, like, I assume we are moving from state 1, okay, to state 2. Are we together? Are we together? Are we together? Listen carefully. I want to explain something now. If K, whether if you like, have P1 V1 is equal to K. That's meaning K1. True of us. P2 V2. We give you the same K2, right? P3 V3 will give you K3. But K1 is equal to K2 is equal to K3. True of us, because it's constant at any point, right? What it means that P1 V1 is equal to what? P2 what? V2. Did you understand what I said now? Come closer, you. Come closer. Come closer. Let me use her note. I said that we have got to hear that what? We've got to hear that what? K is equal to what? PV. True of us. This is constant. What means that remember the Boyle's law is at constant what? Temperature, right? So at any temperature you like, just get the pressure of a gas and its volume will give you constant. This constant means a particular value. It will give you the same value. Okay? Anytime you multiply the temperature and pressure of a gas, it will give you the same value at a given what? Temperature. That's the meaning. What it means that if you like increase the volume, because as you are increasing the volume, the pressure will do what? Decrease. So it will give you the same value. If you like decrease the volume, pressure. If you decrease the pressure, the volume will do what? Increase. It will give you the same value. So if you multiply them, it will give you what? The same value. So if that is the case now, that means if you are moving from one state to another state, let's say from state 1 to state 2 or state 3, you have, if you move from, let's say state 1, if you move from state 1, that means you have what? That K1 is equal to what? P1 what? V1. True of us. State 2, K2 is equal to what? P2 what? V2. State 3, K3 is equal to what? P3, V3, and so forth. But these constants are the same thing. K1 is equal to what? K2, which is equal to what? K3. So if K1 is equal to K2 and K equal to K3, and K1 is P1 V1, K2 is what? P2 V2, K3 is what? P3 V3. That means that P1 V1 is equal to what? P2 V2, which is equal to what? P3 what? V3. That's where we got this relationship in Boyle's law that what says that what happened? P1 V1 is equal to what? P2 V2. Have you seen a thing like this in Boyle's law? This is how this was proved. So this is the equation used to solve question in Boyle's law, that P1 V1 is equal to what? P2 V2. Is it clear? Is it clear? Is it clear? Can you put this down in your note now on your own? Do you not understand it? Are you sure? So this is the formula used in solving question in what? Boyle's law. Are we together? Good. Now, if that is the case now, we have described what? Boyle's law. We have described what? Boyle's law. But something remains. How does kinetic theory explains Boyle's law? How does kinetic theory explains Boyle's law? So let's see how kinetic theory explains Boyle's law. After that, now we'll now solve a question. Then we'll see how far we can go in past question before it is we call it a day. Now, let's look at how kinetic theory explains Boyle's law. Now, if you get something like this, you do know syringe. Okay, now let me know. Do you know? Remember what I told you about gases? That gases are compressible. Remember, you can, if you put a gas in a container, they will spread inside the container, right? You can compress them to smaller volume. True or false? But for liquid, you cannot compress liquid. Instead, the container will burst. True or false? Try to push it together. The container will do what? Burst. But gas, if you can compress it, it will be smaller. Now, when this gas, let's assume you have something, you have a syringe or pasting or something that you can push in and draw out, push in and draw out. You have inside a container. You have a container, small container, and the container is sealed with something you can push in and draw out. That means as you push in the thing, just the same way you press your syringe now. As you push in the thing, if you fill that container with gas, and as you push that thing, the volume of the gases inside there will be smaller, right? Remember that the pressure of the gas exerts on the wall. If that volume occupied by that, if the volume is now becoming smaller, the gases will be struggling inside. They will exert more pressure on the what? Container. Do you know why liquid will burst the container? The liquid will exert pressure, but because the liquid is heavier than gas, they can burst the container, right? But the gas will compress. Now, as they compress it, they are exerting more pressure on the wall of the container. So, did you decrease the volume or increase the volume? Huh? Did you decrease the volume or increase the volume?
Increase the volume of gas.
When you are pushing that thing inside.
Okay, you're increasing the volume.
Increasing, what are you saying?
Wait, is it when you're pushing the gas?
I told you that. Yeah, yes. Are you increasing the volume or decreasing the volume? Huh? 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 Increase it. No, you don't understand what I'm saying. How do I explain this now? Okay, let me use this in this textbook. Look at this thing. Look at this thing in this textbook. Look at it. Look at it. This it started from here, right? This is a container, and the mouth is sealed with something that you can push in and push out. True or false? Now, if you it's like this now. If you push in, the gas is there. This is the volume. This is the entire volume of the gas occupied, right? And there is a particular pressure on the wall here, and this is at and temperature. You would not heat anything. Did you see heat here now? You're not applying any temperature. You kept it at a constant temperature. But now, if you push this thing down, will this volume increase or decrease?
Decrease.
Eh?
Decrease.
It will decrease, right? See it here now. It has decreased. Do you think what happened? Do you think the gas here will mount more pressure on the wall or less pressure?
More pressure.
It will hit the wall more, right? Just like when people are here now, as we're here now, you come and push us together. We want there will be pressure, three of us. You'll be sweating. You're struggling, three of us. So these gas there are struggling in this smaller volume. So that means the volume is small and pressure is what? Much. Is that not Boyle's law? You have reduced the volume, but the pressure is what? Much. So you have this is Boyle's law. True of us. Now look at the second one. When you now draw this thing backward, you will increase the volume, right? We like just as separating us. We do like this. Would there be much pressure? You have increased the volume. Pressure is now what? Decrease. That's why Boyle's law states that at constant temperature, the volume of a gas is the volume of a gas is inversely proportional to what? The pressure. So as the volume increases, the pressure will do what? Decrease. But as the volume decreases, the pressure will do what? Increase. So volume now, but go pressure now, but volume now, but pressure now again, and now but go. The same thing, pressure now, but go volume now, but then pressure now, but volume now again, and now but go. Is it clear? Have you now seen how kinetic theory of matter explains what? Boyle's law. Does it make sense? Does it make sense? So I think we'll stop here for now. Let's see. If you have any question, ask. Let's see if we can answer one or two questions before we stop for today. At least we have 28 minutes to go. So now, with this now I say that, do you think you can solve any calculation on this using P1 V1 is equal to P2 V2, right? I put down this question. After solving this one, we'll go to past question and see whether we can. This question is from Ababio. The example there from this new school chemistry, page 81. Put down the question. It says 375 cm cube of a gas. 375 cm cube of a gas has a pressure of 770 millimeter mercury. Has a pressure of 770 millimeter mercury. Full stop. 770 millimeter mercury. Full stop. Find its volume. If the pressure is reduced to what? To 750 millimeter mercury. Find its volume. If the pressure is reduced to 750 millimeter mercury. Remember what I told you about from one state to another state, first state to second state, that is changes in volume and pressure. So use P1 V1 is equal to P2 V2 to solve this question. Fast. Tell me the answer. Do it now. Tell me the answer fast. Alpha, are you done? Use P1 V1 is equal to P2 V2 now. You not use the formula here. Didn't you see the formula I gave here? Hmm? Jude, use it now. Hmm? Anytime you're given anything to solve, first pull down solution. It will show the person that you started. Cancel down all this is you wrote there. Start from here. Put solution. Then write down the formula I gave you people. Mhm, mhm. It's equal to P2 V2. P1 means first pressure. V1 means first volume. P2 means second pressure. V2 means second volume. So from this question now, which one is the first pressure? First pressure. From this question I gave you. Hmm? For this question, which one is the first pressure? Hmm? And now put it there now. Write the unit to. Mm-hmm. V1 is what? V2 is what? You're not writing the unit. What is the unit of pressure in the question? Write the unit, the millimeter mercury now. mmH, Hg. If you write the figure, write the units. mmHg, that's the abbreviation. Capital H. Uh-huh. The same thing with the other one. M is small letter, or H is capital letter. But that one is no, that one is volume now. What is the volume you're giving? Oh no, CM cube. CM cube. Write C, write M, then cube now. Good, good. That's what you wrote is CM squared though. Cube is 3 now. Good. So now, what is the V2 now? V2 is not here now. That's what I'm looking for because we are still to find the volume. Is the volume of pressure we have to find? The volume that define the volume when the pressure. So we are looking for the V2. So if you put V2, if you put the one you're looking for, you put question mark now. That's what you're looking for, is it not? Mm-hmm. Now substitute all these things in this formula you wrote here and find V2. Turn over now. Then substitute all these things you wrote in the formula. So substitute them there. Millimeter mercury. Mm-hmm. Times what? V1 is what?
So,
Huh? From the question, V1 is what?
CM3.
What is the value first now, before the unit? What is the value of the V1 in that question I gave you? Maybe you have listed it out now. What did you list out here as V2? Huh? What did you list out here as the V2? It's not 375. We're not the one that wrote this. 375 cm cube. It's not. Then put it there now. Fast. Put it there. Let's solve this. 375. 375 cm cube. Is now equal to what? I said you should. What are you doing? It's not. Look at the formula you wrote here now. That P1 V1 is equal to P2 V2. Carry all these things now. Wherever you see P1, you put the value. Whatever you see P1, you put the value. So you can find V2. You don't understand? You don't understand what I'm saying? You have already said that this is the formula. P1 V1 is equal to P2 V2, right? Then P1 is 770. You go from the question. You wrote that P2 is 750 millimeter mercury. You got that V1 is 375 cm cube. Did you cancel this in? Then V2 is what I'm looking for. Everywhere you see P1, you pick the value. Everywhere you see V1, you put the value of V1. Anywhere you see P2, you put the value of V2. It's not. That's what we mean by substitution. So put all these things here now. As you are put it there, complete it. It's now equal to what? This is equal to P2 V2. So this is now equal to what? Huh? Okay, well, so what should be here? There. 750 what? Times what? Times what? Go back to your formula now and check what should be there. Times what? Go back to your formula. Times what? Huh? Which one is the formula you're using? Point the formula you're using first. Let me even know whether you will know the formula you're using. Point the formula you're using. Point it. Let me see. Which one? Huh? Which formula are you using? Huh? Is this not the formula? Jude, is there any issue? Is it not the formula you're using? Huh? So put it here now. What should be here? You need to check the formula and tell me what should be here. Is what?
V2.
put it now. Is there did you have any value for V2? That's what I'm looking for. So just put V2 like that there. Put it like that, V2. So we are looking for V2 now. So make that V2 the sorted formula. Do you know how you make it the sorted of the formula? You don't know. Okay. Since you are looking for V2, that means you divide this 750 is the coefficient of V2, right? You know you know what coefficient is. So if you are looking for V2, you divide both sides by coefficient of V2, so you can find V2. I do it. Divide both sides by the coefficient of V2. Do it. Let's see. Just rule now. Just draw the line and write. Divide. What is the coefficient of V2 here? What is the coefficient of V2 here? You don't know. The coefficient of V2 is 750 now. So divide both sides by 750 millimeter mercury. Just on the line here, write 750. On the line here, write 750 and cancel out. I do it. I can cancel out. You will take this thing home and do it at home. I will see you tomorrow. Okay? Then we'll talk more on that. Did you hear me? Go home and continue that thing. We'll talk more on that tomorrow. Okay? So we don't waste our time here. Okay? Go home and read that thing very well. Get your textbook. Look at it very well. Look at it critically. Tomorrow you tell me what happened. Did you hear me? So we don't waste our time here. So let me see your own. Okay, the answer is 385. Good, you got it. All right. Oh, our time has even elapsed. We just have 9 minutes to go. So in our next class, we'll continue with Charles' law. Okay. We are done with Boyle's law. I wanted us to solve questions, but we don't have time again for it. Maybe in our next class we'll start with calculations and pass question on this. After we'll now go into Charles' law. That's be in our next class. There's no time again. Please, if you go home, study what we did today again. Okay? Study everything we did today. Study, revise your note. Hope you're listening. Revise your note. Study all these things we did: boiling, freezing, Brownian movement, diffusion and osmosis, and latent heat and or fusion and latent heat of vaporization. All these things we described. Then kinetic theory of gases. Then Boyle's law. Revise them again. Okay. So, if possible, try to go into Charles' law a bit. Try before our next class, so that when I'm explaining it, it will be easy for you to do what? Understand. Okay. Any question? Any question? All right, we'll stop here for today. Thank you very much for your attention. Tomorrow is what? Wednesday. What do you have tomorrow? English language. Okay. We'll stop here in English language. We are still in what?
Synonym.
Okay. Okay, we'll see how far we can go there. All right. God bless you.